Okay, we will continue our discussion on algebraic geometry. Okay, in the previous classes, we've been talking about a new kind of classification of conic sections, isn't it?
Yes.
A classification based on purely algebraic ideas, not based on any geometric ideas. Today, actually, I wanted to continue that discussion in the direction of in a new direction, especially discussing affine transformations.
Okay.
That's what I wanted to discuss, but there is a slight change of plans.
Okay.
Because today I wish to discuss some basic elementary ideas from mathematics.
Okay.
That you probably actually would know this stuff. Many people who are seriously getting into mathematics already know this stuff. But anyway, I'm going to discuss that because these ideas are widely used across all fields of mathematics. It's such a basic level, kindergarten level idea. I'll share my board. Right. The topic is equivalence relations.
Okay.
Equivalence relations. Equivalence relations and quotients.
Quotients. Okay.
Quotients. Okay, this is a very basic kindergarten level idea in mathematics. Maybe below kindergarten. It is that basic, but it is used across various fields of mathematics, especially quotients. The idea of quotient is one of the most important concepts in mathematics. Okay, quotients appear in almost every branch of algebra, geometry. Like quotient groups. Quotient groups is an example. Quotient groups or quotient spaces. Quotient spaces or quotient spaces in linear algebra. Also in topology.
Okay.
Okay, which is also in topology. It's also known as identification space. Identification. Okay.
Okay.
And in many other fields of mathematics, like projective plane. Projective plane is very important kind of quotient that we will be discussing in this course. Projective plane is a complex, for instance, complex projective plane. Complex projective plane. Complex projective plane. CP2 is actually a quotient. It is complex, three-dimensional complex vector space without the origin, modeled out by an equivalence relation known as the scalar multiplication.
So you're just spitting out jargons now.
Okay,
So
I'm telling you that these
yeah,
ideas
it's
are
very
very important. Okay, that's what
important.
I'm telling here. Okay. Also, homology is a quotient. Cohomology is a quotient. Many quotient groups and many quotient fields. Many ideas in mathematics are quotients. So, okay. So this concept is very important. That's what I'm telling. Okay. Okay. So in order to study quotients, we need to understand equivalence relations.
Okay.
Okay. When you exactly pin down the idea of equivalence relations, quotients is just an extension of that idea. Okay. Quotients are just a set of equivalence classes. So in order to understand equivalence classes, we need to understand equivalence relations. And in order to understand equivalence relations, we need to understand what a relation is.
Okay.
Relation. A relation is nothing but a subset of Cartesian product. Relation is a subset of Cartesian product. Let me write it more neatly. Relation. Relation is a subset of
Cartesian products.
Cartesian product. Okay, let me give you an example that will make the idea clear. Okay, consider, I have written an example here. Okay, let A be a set. Let A equals some names like Alex, maybe Jonan, your own name, then maybe Bobby, then some David or some names. Okay, David, give me another name, Joe.
Joseph.
Okay, Joseph. Okay, some names. Let B be a set of some alphabets like A, some letters A, B, C, D, and E.
Okay.
Okay, I'm going to define a relation. Let R be a relation.
Okay.
Let R be a relation given by R is the set of all ordered pairs x comma y. Since Cartesian products contains ordered pairs and relations are subsets of that Cartesian product, elements of relations are always ordered pairs.
Ordered pairs.
Okay, set of ordered pairs such that the word x starts with the letter y. Word x starts with the letter y, where x belongs to A and y belongs to B. Okay.
Okay.
Okay, so in order to find the relation, we need to first find the Cartesian product of A and B. Okay.
Okay.
So we will do that first. Okay, our relation was the word x start with the letter y. So what ordered pairs will be in our relations? In our relation, Joe.
Alex A, Bob B, Dave
Okay,
D.
Alex A will be in the relation. Let me use a different color, maybe orange. Okay, Alex A. Then
Bob B,
Bob B. Okay, that's correct. Then
Dave
David,
D.
Dave D. That's it, right?
Yeah.
Okay, out of all of these ordered pairs, which I just uh, wrote with such difficulty, only 3 appear in our relation.
Okay.
Okay, that's what our relation is. Our relation is this set of ordered pairs, Alex, comma A, Bob B, comma B, and David, comma D.
Okay.
Now this set, we can see that this is a subset of this entire
A.
Cartesian product.
Yeah.
Okay, this is actually subset of A cross B. Okay,
Okay.
this is what a relation actually is. It is a subset of a Cartesian product. Okay,
Okay.
if the
Okay.
end, okay, Joe.
Let me ask you another question. So, if what's the difference between a relation and a function?
A function is a relation in which every element of the domain has a image in the codomain. Let me be more clear about those terms. What's a
Okay.
domain? Domain is the domain is the set. Domain of the relationship R is the set A.
A.
Co-domain of R is the set B. And range of R is the set of all images in B, meaning the set A, comma B, comma D. These elements.
Okay.
Okay. Okay, Joe.
So domain is a set of names. Alex,
Yes.
Jonan. Okay. Codomain is the set of what uh,
Letters.
letters. So range is the those elements in B which take
Present
parts in
in
take part in
relation,
the relation.
which
Okay.
are related to the elements of A.
Okay. Okay.
Okay. If all of the elements in the domain have an image, meaning it can be
Range and range and codomain will be the same.
no.
Mhm.
Uh, Not range and codomain, meaning every element of the domain is present in the ordered pair. Here
Every element.
is the
Okay.
domain. Okay, what's the domain here? Here the
A.
domain is
Alex.
A is the set. Alex, Joe, Bobby,
Dave.
then one Dave and Joseph.
Sure.
Okay.
Okay.
Okay. If you want to sleep, just sleep, Joe. Okay. Okay. Now we have the letters A, B, C, D, and E. Okay, we can map. This kind of an arrow representation give a sense of direction here.
Yeah.
A to B. Okay,
Okay.
R is defined from A to B. So Alex to A, Joe to no elements, Bobby to B, Dave to D. That's it.
Okay.
Okay. Here Joe and Joseph has no image in B.
Okay.
So this relation is not a function.
Okay. Okay.
A relation becomes a function if Joe is mapped to Joe and Joseph is mapped to some J here.
Okay.
But here, no, there is no J here.
Okay.
So this relation is not a function.
Okay.
Okay, relation becomes a function. Relation becomes a function.
When every element of the domain is mapped to
An element in B. If every element of A is mapped to an element.
in B.
Okay.
Okay.
Okay, if okay, this relation is a subset. We have seen that the relation is a subset of the Cartesian product. What if every element of the Cartesian product is present in the relation? Meaning all of these ordered pairs are present inside. Such a relation is called a universal relation.
Okay.
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 If the relation, if no element of the Cartesian product is present, then the relation is called a empty relation.
Okay.
Empty relation. Empty relation when R equals okay.
Okay.
If
Let me ask you. Does is universal relation can be considered as a function? One to many function, isn't it? Many to
one
many
to
because Alex will be mapped to different values. Alex will be mapped
yes,
to
Joe. Thanks for pointing out that thing. Okay, it will. That's a thing that I forgot to mention. Everything should be mapped to an element, but one element should have only have one image. Okay, that's also a condition here.
okay.
Yeah, let me write that. I forgot about that. Okay, in B and one element in A should only have one image
One.
in B.
Okay.
Okay, but we should also add that definition to our definition of a function. Okay,
So okay.
okay, Joe.
Yeah, understood.
Okay, so this is a very important. Thanks for pointing. Thanks for completing our definition. Okay, I only wrote partial definition. Okay, this is the definition of function. Okay, now in mathematics, we are actually concerned with the relation that is defined within a set. Okay, we are more concerned with the R subset of A cross A.
Okay.
Okay, Joe?
Yeah.
Okay,
Relations between
in relation from a
relation
set to itself,
to a set to itself.
or
Okay.
relations between elements within a set.
Okay. Like
Okay,
real numbers,
any set,
complex.
it can be any set. Okay, it can be set of names or set of. But in computer science, if you are talking about coding and writing algorithms, the relation between two sets come up often.
Mm.
Okay, but in pure mathematics, many of the relations are concerned with that we are concerned with are actually between elements of the same set. Okay,
Okay.
in such a case, new kind of definitions uh, can arise, like transitivity, reflexivity, and symmetry and anti-symmetry. These kinds of ideas. Because look at these two ideas: universal relation and empty relation. A universal relation, these two ideas are based on how many elements are present in R, correct?
Yes.
It
Yes.
doesn't tell anything about the nature of the relationship.
Okay.
Okay. There is a drawback of if you are going to classify a relation based on whether it is a universal relation or empty relation or just a normal relation. If you are going to classify a relation based on that, it doesn't tell anything about what kind of relationship are we talking about. Okay, so for that we need new definitions like reflexivity, reflexivity, then transitivity, and symmetry or anti-symmetry. Well, today we will only focus on symmetry. These two ideas are very important in order to define equivalence relations. So let's look at them. Reflexive relation. Okay, let's look at a relation. Let A be the set 1, 2, 3, and R be a relation 1, 1, 1, 3, 2, 2, 2, 3, and 3, 3. Okay,
Okay.
Joe, make a Cartesian product of on your own. Okay, make a box, make a
Okay.
multiplication table. Okay, so that you can see the patterns that we are going
Yeah.
to discuss.
1, 1, 1, 2, 1, 3. Then 2, 1, 2, 2. Okay, got it. 1 second. Let me just.
Okay, we are going to find A cross here. So 1, 2, 3 here, and 1, 2, 3 here. 1, 1, 1, 2, 1, 3, 2, 1,
1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3.
Let me make a copy of that because we will be using it often. Okay, let me paste it here. Okay, in this product, what elements, just mark the elements that are present in the relation. Here 1 comma 1 is present, isn't it?
Yeah.
1 comma 1 is present. 1 comma 1 is present. Then 1 comma 3 is present. Then 2 comma 2 is present. Then 2 comma 3 is present. Then 3 comma 3 is also present.
Yes. So is 1 comma 1 is present. 1 comma 1 is present. 1 comma 3 is present. 2 comma 2 is present. 2 comma 3 is present. 3 comma 3 is present. Yeah.
Okay. Here, if you look carefully, we can see that every element of A is actually related to itself. Meaning all the diagonal elements of the Cartesian product are present in the relation.
Yeah. Yes.
All these diagonal elements are all present here. Okay, diagonal. The diagonal elements. Diagonal elements are 1 comma 1, 2 comma 2, 3 comma 3. Okay. Okay, Joe.
Yes.
Such a relation is called reflexive. Such a relation is called reflexive. More formally, if every element of the set is related to itself. Formally, every ordered pair,
Ordered by XX.
exactly, every ordered pair x for all x belonging to A is present. If present in R, relation R, then R is reflexive. Okay.
Okay.
Okay, let me give you an example. Okay, you just do it yourself, just a problem, like problem. Okay.
Mm.
If R is the relation ordered by x comma y such that x will always be greater than or equal to y, defined on the set A equals 1 comma 2 comma 3 comma 4. Okay, is this question, is this reflexive?
Yes.
Why?
Because the condition is x is greater than or equal to y, which implies that x can be equal to y. So there is xx elements for every x. For every x, there is also an x. Or
Exactly, answer it is it is reflexive. It is reflexive. Okay, idea is very straightforward. This is a very straightforward idea.
yes.
Okay. Okay, let's move on to the next. Maybe I think we need this. We need this Cartesian product. That's why I made a copy. Okay, let me place it here. Okay, let's move on to the next idea. That is uh, symmetric relation. Symmetric. Again, let me give you some examples. Consider the same set A equals 1, 2, 3. So we can use the same Cartesian product 1, 2, 3. And let's look at some relations. First relation, R1 equals 1, 2, 2, 1. Then R2, okay, let's first look at R1. Okay, let R1 be a relation defined on A. Okay,
Okay.
so let's move on. Let's again consider our Cartesian product here and mark the elements. Okay, Joe.
Okay.
I'll make some copies because we need this. Okay. Okay, Joe. Let's mark those elements. 1, 2 is here. So 1, 2 is here. Then 2, 1 is here. Okay.
Okay.
Here, the we can see that these two elements are diagonally opposite pairs. Isn't because this is the diagonal line. These are the diagonal elements here.
Okay.
And 1, 2 and 2, 1 are diagonally opposite to each other, isn't it?
Yes.
Such a relation is called symmetric. That's it. More formally, if if such a relation, let me write here 1, 2 and 2, 1 are diagonally opposite pairs. Opposite pairs. Okay. Diagonally opposite pairs means xy and yx. Xy and yx. Okay.
Yeah. Okay.
Such a relation is called symmetric. Symmetric relation definition. Definition: if for a if for every x comma y element of R, its diagonally opposite pair. Its diagonally opposite pair
Or we can say,
yx is also present. Is also present in R. Then R is symmetric. Okay. Okay.
okay.
Okay. Now observe that here 1, 2 and 2, 1 are not the only diagonal pairs, right? Here 1,
Yes.
3 and 3, 1 are also diagonal opposite pairs.
Yes.
But those pairs are not present in your relation.
Yes.
But that's okay. Because the definition is it's an if statement.
If. Okay.
Okay. If xy is present, yx should also be present.
Also be present. Okay.
Okay. If xy is not present, yx, there is no need for yx to be present.
Okay.
Okay. For instance, let's look at another relation, R2. R2 is 1, 2, 2, 1, and then 1, 3. Is this relation symmetric?
No,
Why?
because there is no 3, 1.
Exactly. Let me place that board here. Here, 1, 2 is present. Then 2, 1 is present. And 1, 3 is present. But 3, 1 is not present. Okay. Okay. So it is
Okay.
not a reflexive symmetric. Okay, Joe?
Okay.
Okay, let's look at another relation, R3. You tell me whether it's a reflexive, whether it is symmetric. Okay, 1, 2, then 2, 1, then 1, 3, and then 3, 1.
It's reflexive. It's not reflexive, it's symmetric.
It's not reflexive, but it's symmetric. It is symmetric. Okay, let me give another example. R4 is, look carefully, it is just 2, 2. Is this symmetric?
Yes, it's symmetric and reflexive.
No, it's not reflexive because not
Oh,
all
yeah. All elements.
all diagonal elements should be
Elements
present
should be present. Okay, yeah.
for it to be a reflexive relation.
Okay. If there is two, it's symmetric.
Why is it symmetric?
2, 2, 2, 2.
Exactly. Okay. If here x and y are the same,
Yeah.
so xy is present and yx is present here because x and y are the same. This is symmetric. Okay.
Okay.
That is what symmetric relations. That is what symmetric relations. That's it. Okay. Let's move on to our next. Okay, let me give you one more example. Maybe you can. It is 2, 2. Look carefully. 2, 2, 1, 3, and 3, 1. Is the symmetric?
Yes.
Why?
For every x comma y, there is a y comma x.
Yes, exactly. Here we can see that 1, 2, 2 is present. 1, its diagonally opposite pair is 2, 2 itself.
Yes.
Then 3, 1 is present. 1, 3 is present. So this is symmetric relation. This is symmetric relation. Symmetric. Okay, Joe, let's move on to our final case, transitive relation. Okay, I want to discuss it in detail. It's a very important case, and we are going to discuss transitive relation in a really novel way, in a really new way. Okay.
Okay.
Transitive relation. Okay. For that, I am going to define a new algebraic product here. It is called a transitive product. It is a new kind of definition. It is a purely algebraic definition. It is a very interesting. That's why I want to discuss this topic. Okay, new definition. New definition. Transitive product. Transitive product. Okay. I use the symbol like this. I can't come up with anything. It's look like a Japanese anime type thing. But if you have any symbol, just suggest me. Okay. The transitive product. It's very important. It's a new kind of definition. We can define transitive product in terms of that product. It is very simple. The transitive product of transitive product of ordered pair x comma y and ordered pair y comma z is, we are going to take products, meaning we are creating algebra here. X comma y multiplied with y comma z will give me the ordered pair x comma z, meaning y is gone.
Okay.
Okay. Here the term, when here the letter y is actually deleted.
Okay.
So that x becomes here, x comes here and z comes here, and y is gone. Okay. For instance, example 1 comma 2, if we take the transitive product with 2 comma 4, what will be the answer?
1/4.
Yes, 1 comma 4. Okay. Some I'm going to discuss some of the algebraic properties of this product. Some properties.
Okay.
Some properties. The most important property is not all ordered pairs can have transitive product.
Okay.
Not all ordered pairs
Have transitive product.
can have transitive products. For example, A comma B and C comma D cannot have transitive product. This product is not possible.
Why? Oh yeah.
Why?
Yeah.
Because
It's
Y
not
and
common.
the Y's here are different.
Yeah.
Okay. This product is not possible. It is not possible. Okay.
Okay.
Second property is, for every ordered pair x comma x, the transitive product with itself is always possible.
Okay.
With itself is always possible, which is the ordered pair itself. That is x comma x or x comma x multiplied with x comma x will be x comma x. Okay. Does this resemble anything? Any algebraic thing?
Identity.
Yeah. Okay, we will see more of that thing in this new this some okay, let's continue. Okay. Now, if you have a if we have say let's look at a Cartesian product like this one. Let's take this Cartesian product. Now let's take an diagonal element. Okay.
Okay.
Let's take a diagonal meaning x comma x's. X comma
Okay.
x. Diagonal element. Okay. Let's take a diagonal element. Take a diagonal element. Joe,
Okay.
just pick a diagonal element.
2, 2.
Okay, example 2 comma 2.
Okay.
And I am going to mm, multiply it with uh, 1 comma 2.
Okay.
Okay, consider the product. Product 1 comma 2 times that diagonal element 2 comma 2.
Okay.
What will be the answer?
1 comma 2.
1 comma 2, meaning the x comma x's are indeed the identities here.
Okay. Only
Okay,
when they are multiplied second, isn't it?
no. Let's 2
Take
comma
1.
2. Let's take another product with 2 comma 3. What is the answer?
Okay. Yeah.
What is, you got it?
So, yeah, got it.
Will always give that product, that uh, that ordered thing. Okay,
Okay.
so that's our third property. The diagonal elements. Isn't it interesting?
Yeah, it's interesting.
Diagonal elements act
As I did.
like
I did.
identities. Okay, so we have identity. So the next important algebraic thing is, what is it? Say we are studying group theory. We have identity, then
0.
0 is the identity.
Oh, okay. Inverse.
Oh, yeah, exactly. So we need to talk about inverses. Are there inverses here? Okay. If inverses are here, this is a legit algebraic idea. Okay.
Okay.
Surprisingly or not surprisingly, there are inverses here.
Okay.
Okay. To show that, let's
Off
pick an off
diagonally
diagonal element. Exactly. Let's pick a
diagonally
diagonal
opposite.
opposite. Consider two diagonally opposite pairs. Like Joe, pick two diagonally opposite pairs.
2, 1, 1, 2.
Okay, 2 comma 1. When multiplied with 1 comma 2, we get what?
2, 2.
2 comma 2, which is the identity. Okay,
Okay.
this shows that the diagonally opposite pairs are inverses of each other. Okay,
Okay.
and finally, the last property is transitive product is not commutative. I mean, that's obvious at this point,
Yeah.
right? Transitive product is not commutative. That is 2. So let's take this product 2 comma 1. When we multiply it with 1 comma 2, we get 2 comma 2. But if we reverse the order of multiplication, 1 comma 2, when we multiplied with 2 comma 1, we get 1 comma 1, not 2 comma 2.
Yes.
Okay,
Okay.
both of them act like identities, but they are not the same. This shows that it is not a commutative product. Also, it is not all elements can have transitive product. That is the main main thing that keeps this idea from being a legit algebraic thing. Because in group theory, for instance, in group theory, every element can be multiplied with any other element.
Yeah.
This is that same for rings or fields or any algebraic object. Vector spaces, we can add any two vectors with each other. But in this case, that it is not possible.
Okay.
But still, there is some proto algebra here.
Yeah, some semblance of algebra.
Some resemblance of algebra. Okay.
Okay.
And we are going to make use of that to define our transitivity. I think this is a new way of defining transitivity. Okay. A relation is said to be transitive if every possible transitive product is present. That's transitive relation. This is a new, purely algebraic idea. Transitive relation. A relation is said to be transitive. A relation is said to be transitive if every possible transitive product is present. Okay, let's look at two or three, few examples.
Okay.
Okay, let's look at the set example. Consider the set A equals 1, 2, 3, 4.
Okay.
Okay, let's first find the Cartesian product. Okay, A cross A, 1, 2, 3, 4, 1, 2, 3, 4. We have 1, 1. We have 1, 2. We have 1, 3. We have 1, 4. And we have 2, 1. We have 2, 2. Okay, we have 2, 3. We have 2, 4. We have 3, 1. 3, 2. 3, 3. 3, 4. 4, 1. 4, 2. 4, 3. And 4, 4. Okay, let me first make a few copies. Okay, that's enough. Okay, Joe, I'm going to give you a. Okay, let's first look at the diagonally opposite pairs. What are the diagonally opposite pairs here? 1, 1. Okay.
1, 1, 1 to 2, 1. Then okay, 2, 2. 3113, then 3 comma 3, 4114, 3223, then 4 comma 4 to 43, 34, 4224.
Okay, these are the diagonally opposite pairs. These two, then these two, then these two, then these two, these two, and these two. Okay, all of these are, we can take transitive product for all of them, right?
Yes.
Mm.
Yes.
For instance, we can write transitive product for say 1 comma 4. We can find the transitive product with 4 comma
4
1.
comma.
We will get the answer 1 comma 1. Or we can also find transitive product with 1 comma 4. We can also find transitive product with 4 comma 3. Okay,
Okay.
we will
This
get
will go.
1 comma 3. Hmm?
Okay.
Okay, we have defined that a relation is said to be transitive. Every positive transit, every possible transitive product is also present. Okay, so let's look at a relation. I'll give you a relation. Joe, you should tell me whether it is a reflexive transitive relation or not.
Okay.
R1 equals 1 comma 2, then
Okay.
2 comma 3, then 1 comma 3.
Yeah.
Joe, what are the positive transitive?
1
Positive.
comma 2, 2 comma 3. It will give you 1 comma 3.
Yes, 1 comma 2 multiplied with the 2 comma 3
It will
will
give
give
you
you
1
1
comma
comma
3.
3. Okay, then
Mm,
uh, that's it.
yeah,
Okay,
that's it.
that's it. So we can. Oh, actually, I forgot to mention another important thing. Let's look at this product 1 comma 4 and 4 comma 3. Okay, let me take another box and put it here. It's a very important idea here. I'm so thankful for external. It makes actually note taking very easy. Okay, let me make it this. Okay, can you see it?
Yeah.
Okay, let me take this thing and move it to here. Okay, let's look at that second transitive product here.
Okay.
1 comma 4 and 4 comma 3, meaning 1 comma 4 is here and 4 comma 3 is here. Okay, what is its product? Its product is okay
1 comma 2.
1 comma 3, and also we can take okay, just let's focus on this product 1 comma 4 and 4 comma, this diagonally opposite pairs 1 comma 4 and 4 comma 1, 1 comma 4, 1 comma 4 and 4 comma 1. Okay, okay, what are the possible transitive products? First possible product is resulting in 1 comma 1, and we can also take the product for it is commutative, right? Because
Mm.
diagonally opposite pair. So 4 comma 1 when multiplied with 1 comma 4 gives
4, 4.
4 comma 4. Okay, let's look at the pattern here. Here one, the products are this one and this one, meaning if we take these two diagonally opposite pairs, its product will be like a square. Possible
Yeah.
product will be like a square.
Okay.
Okay, this is true for all diagonally opposite pairs. For instance, if we take
Hello.
okay, Joe, can you see the
Yeah.
board?
Yeah. I can see the board.
Okay, I will Just write it here. Let's consider another ordered another possible product, like 1 comma 3 and 3 comma 1. 1 comma 3 and 3 comma 1. Okay, what are the possible transitive products? 1 comma 3 when multiplied with 3 comma 1, we get 1 comma 1.
Yes.
And then 3 comma 1, we can commute and find the transitive product with 1 comma 3, we get 3 comma 3. Again, those things form like a box here. 1 comma
Yes.
3 and 3 comma 1. This possible products are
Forming a
3
box.
comma 3 and 1 comma 1. Okay, meaning this is like a, there is a kind of interesting pattern here. Okay.
Okay.
Okay, now let's move on to defining relations. We have considered a relation R1 equals 1 1 comma 2, 2 comma 3 and 1 comma 3, and you have said that there is only one transitive product is possible. One, that is 1 comma 2 times 2 comma 3, and that the product is 1 comma 3, which is present here. Okay, since no other whole, the definition is that all transitive products must be present. Here only one transitive product is possible, and it is present here.
Yes.
Okay, so this relation is in fact a transitive relation.
Relation.
That is the idea here, defining relations in terms of this new product. Here only one possible, here only one possible transitive product is possible, which is 1 comma 2 and 2 comma 3. Okay, and the answer is 1 comma 3. It's again like a box. Okay,
Okay.
okay, that's how we can find the possible transit. Just move it like a square, and where you will eventually meet at the transit. Okay, here this 2 comma 2 is not possible, but 1 comma 3 is possible. If you think like a box, this should also be possible, but if you think like a box, it should be possible, but here it is not, but this is possible. 1 comma 3 is possible. Okay,
I'm getting an idea.
okay, think about it.
Yeah, I'm thinking about it.
Come up with new kind of patterns.
So, yeah, these relations usually are showing a geometric patterns also,
Yeah,
right?
exactly. Okay, let me give you another relation. Let me give you another relation R2 defined on the same set.
Okay.
1 comma 2, you just check whether it is transitive. 1 comma 2, 2 comma 3, 1 comma 3, 3 comma 2. First look at all the positive transitive products and then check whether it is present in the relation. If it is not a transitive relation. Possible.
No, this is not.
Okay, let's find all the possible transitive products. What are the possible transitive? 1 comma 2 and 2 comma 3 is possible, which will give the answer 1 comma 3, and that is present here. Then 1 comma 3 can be multiplied with the 3 comma 2 with an answer 1 comma 2, which is also present here. Now then what? Then what you?
Two. Uh,
3
2
comma 2
comma
and
2 comma 3, 3 comma 2.
2 comma 3 and 3 comma 2. Is it present? The
No,
answer
2
is
comma
2 comma 2,
2 comma 2,
which is
not
not
present.
present here. So let's use the same box. Okay, let's look at the possible. Here 1 comma 2 is present here. 2 comma 3 is present in the relation. 1 comma 3 is present. Then 3 comma 2 is present. Okay, now let's draw it like a square boxes.
Okay.
So if we take that these two pairs, let's 2 comma 3 and 3 comma 2 comma 3 and 3 comma 2 can result in these two products. That's it, these two products. If you look at like square,
Yeah.
but both of them are not present here, right?
Yes.
We can also commute this, these two. We can commute this 3 comma 2 and 2 comma 3 can be multiplied to form 3 comma 3, which is not present. 2 comma 2 is also not present. Okay, but here this is present. 1 comma 2 and 1 comma 3 can multiply to get 1 comma 3, which is present.
Yes.
But the definition is that all possible transitive products should be present.
Yes.
So this is not a transitive relation. Okay, that's it. That's it. We are okay. You get the idea.
Yeah, I got the idea.
What
Uh,
is your opinion on defining transitive relations in using these new products?
it's a unique way, actually.
Okay, what are some drawbacks?
No, this seems, for a layman, this seems to be a roundabout way, but if there are some, you know, trade backs.
I think this is algebraically more.
Yeah.
This brings one algebraic clarity because we are just this is like multiplication.
Mm.
We are taking
It's
possible
more like
products.
something like Einstein's notations. Do you remember?
I actually don't remember.
Uh,
Okay,
a,
remind me.
when we usually deal with tensors, aij into tensors, not tensors, summations, aij, uh, aij dot aji is
Oh,
equal
okay, okay.
to
It's like an algebra with indices.
oh yeah,
Okay, it has somewhat similarity, but not exactly.
exactly.
Okay.
Okay, okay. Can we stop here
Yeah,
today?
yeah.
I'm not
Okay.
feeling
We will stop today because it's been. I think it's we
way
took more than 1 hour.
1 hour.
Okay. In the next class, we will define equivalence relations.
Okay.
Okay.